Hello and welcome to our instructional video on functions and their graphs. We are focusing on the definition and the evaluation of functions. We'll begin by establishing our understanding of the function. A function is just a special input-output relationship between two quantities or variables. The first variable or the input is the independent variable and the output is the dependent variable. So there's a relationship between these two, and this relationship is defined by your function. The function is special because it has the property of such that each member of the domain or each member of the independent variable or input is matched with one and only one member of a range. So if a member of the domain is matched with at least two, it's no longer a function. So that's special with functions. We could understand more about the function by imagining the function as a machine like this one, where your your collection of all possible inputs, because not everything can be put into the machine. This collection of all possible inputs is the domain. That's just the name of the basket, and the collection of all y's, the collection of all y's that is matched to each member of the domain. The collection is called the range, and this member of the domain is matched with only one member of the range. So you can imagine here's a machine that from the domain you get an x, you put it into the machine, and you get an f of x equals y. That's your output. But more accurately understanding the function, what really happens is that here you have a basket of possible inputs and a basket of possible outputs. So you put in your x, and then what the machine f does, the function, what it does is it matches one y to each x, and then you get your f of x equals y. This f of x is also called the functional notation. This one, this notation here, it is called the functional notation, and it's like another name for the y because it represents y as being a function of x. It summarizes the relationship between x and y. So there's a functional relationship. You could further imagine a function working like this. So there's a queue. So these are like your domain. Each person in line is an x, and they go to the function, and these two represent the function. They're assigning a y. They're assigning only one y, one relief good to each person. So that's what happens. But where can you see functions in the real life? Well, here's a little situation. Suppose there are two people, two friends. One person comes up to the other and says, "Hey, can you lend me some money? I need 500 pesos to buy something." And then the other person says, "Okay, I'll give you the 500 bucks." So the second guy on the right, he whips out his money, and very excitedly, the first guy gets the money, 500 pesos. So before they went away on their own merry ways, they agreed that the first person, should pay 500 pesos back plus penalty, if any. And they also agreed that the penalty would be 8 pesos per day late in payment, just as much as the minimum fare in the jeepneys. So in our little story, this is what I want to give attention to, this statement of 8 pesos penalty each day late. So of course, we know that for each day that passes, this guy has to pay more and more penalty. And this it's actually given by this equation, and this now is a function. It's actually a linear function. We'll learn about that later. So he has to pay 500 pesos back when the deadline comes, plus 8 pesos times each day late. So the more days he is late, he has to pay more. And you can see that it's a function because for each for each independent variable, there's partnered on one and only one from the range. For example, if D or days late is 1 day late, he has to pay in total 508. If he's late 2 days, he has to pay substitute this 2 times 8 16, so he has to pay 516. If he's late 5, then he has to pay 540. And if he's even 10 days late, he'll have to pay 580 pesos. So you can see that one member of the domain is matched with only one. So that's why it's a function. And P, or the payment, is a function of D. How about this? Is y squared equals 4x a function? Let's see. Let x be equal to 1. So if x is equal to 1, you'll have y squared equals 4 times 1 because you just substitute x with 1. And with from here, we get y squared equals 4. And to remove this exponent here, we square both sides of the equation. We get square root of y squared and positive plus minus square root of 4. So we have y equals to positive minus 2. But here's what's interesting. This is now no longer a function because let's um, let's explore that a little bit. Here you have the domain and the range. X, your x here was 1. And y1 is, say it's positive 2, and y2 is negative 2. So this is in the domain, and these are in the range. As you can see, 1 was, when you let x be equal to 1, it is now mapped, it resulted in 2 and negative 2. So it is matched with not 1, but 2 elements, members of the range. Therefore, y squared equals 4x is not a function because at least one member was mapped to two members of the range. That's why this is not a function. And talking about functions, we usually encounter polynomial functions. And polynomial functions are all of them are represented by this equation right here. F of x equal to a sub 0 xn plus a sub 1 minus 1, so on and so on until plus a sub n. It looks complex, but it could be easy to understand. So all your a's, they're just constants. So real numbers, 1, 2, 3, 1 over 2, 3 over 4. So integers and fractions, they could be in these uh, positions over here, these constants. The only condition is that the very first a cannot be 0. So the a that is attached to the x with the highest exponent. So these x's are just arranged in a manner that the x with the highest exponent is to the left, and then the next x with the highest exponent. So suppose this is x to the 5, then this would be 4, it will be 3, 2, 1, 0, until the very last term, which is just a constant. So that's it. So you have terms that have constants, and the x's are all just decreasing in number until the very last term is just a constant. For example, f of x is equal to 3x plus 1. So here we have, this is your a sub 0, and your x starts with 1. So x n minus 1. Obviously, the next x would be x sub 0, so there's no more x. This is your last term, the last term, the constant. See? This standard equation can represent this equation. So this is a linear function. How about this one? 5x squared minus 22x minus 2. This is your first term where the highest exponent is 2, and the next would be 2 minus 1 is 1. Right, so here, x sub 1 until your constant in the end. This is now a quadratic function. And here we have a rather large one, so I intentionally put this here. See, as you can see, the x with the highest exponent is the to the leftmost. So look, 7, 6, 5, 4, 3, 2, 1 until 0. And all those a's, they are just constants. Here we have -1 and -1. See? So this expression here represents this too. And this and these three also have you may encounter questions tackling with what is the degree of the function. Here, to know the degree, you just look at the highest exponent. So here, the highest exponent is 1. So the degree of this function is 1. The degree of this function is 2 because that's the highest. The degree of this function is 7 because that's the highest. So now we'll have an example of functions. So let's let h of x be x cubed plus the square root of the quantity x minus 1. So the question is, what is h of 2? What is the value of the function when your input quantity, your independent variable is 2? What happens? And also there is further a question, what is the domain and the range of h of x? So those two, the illustration I gave you a while ago, what are those two baskets? What are the numbers inside those baskets? And here is our example. H of x equals this expression. So the first task is to evaluate h of 2. So h of 2, what we do is just substitute to all the x in the expression the number 2, because that's what's given. So your x cubed becomes 2 cubed, x minus 1 becomes your 2 minus 1, and evaluating 2 to the 3 is just 8. 2 minus 1 is just 1. So 8 plus square root of 1 is just 9, right? That's easy. How about the domain and the range? So for the domain, as you remember, the domain is the collection of all the x, all the inputs, collection of all the independent variables that you could put into your function. So the clue here is the tip I'm gonna give you is look for radical signs, square roots, cube roots, uh, those kinds, and fractions, because usually from these would come special conditions. For example, in x minus 1, observing x minus 1, could you put any value into x? Any value? Could you put -2 in x? No, we cannot, because if this was -2, this expression will become -3, and then we'll have an imaginary number by then. So we can't have imaginary numbers. So exploring this, x minus 1 should be greater than or equal to 0, because if it's less than 0, that would be negative, right? So x minus 1 is greater than or equal to 0. So transposing this to the other side, we have x greater than or equal to 1. So that's your special condition for your domain. Your domain H is x such that x is greater than or equal to 1, and x is a real number. So this is a set. So that's why it has curly braces. It's a collection of all the numbers that is available to be put into the function. So that's why it's actually just saying this collection, this set, contains x, and the special condition for all the x is that they are greater than or equal to 1, and that they are real numbers. How about the range? For the range, we have to explore a little bit more for the range. Right, so to get the range, I suggest you do something like this. You draw a table where on the top you have the x values, and on the bottom you have the h of x values. So we'll investigate the trend of h of x, as we also put in some consecutive values for x. So let's start with 1. What happens if x is equal to 1? So we substitute x equals 1 to the expression. So h of 1 is equal to 1 cubed plus 1 square root of 1 minus 1. So this becomes 0 and this is just 1. 1 plus 0 is 1. So that's what happens when x is equal to 1. H of x is equal to 1. How about if x is equal to 2? We actually evaluated that here already. So this is what happens with h of 2. It becomes 9. So we put that in here, 9. So how about if x was equal to 3? What happens? So we'll substitute this into our expression. H of 3 is just equal to 3 cubed plus the square root of quantity 3 minus 1. So 3 cubed is 27, 3 minus 1 is 2, and there's nothing more we can do about this. So this is what happens to h of x. So then finally, what happens if x was equal to 4? So we'll see. So let's evaluate h of 4 is just equal to 4 cubed plus the square root of 4 minus 1. 4 cubed becomes 64, 4 minus 1 becomes 3. And there's nothing more we can do about this, so that's why we put it in here, 64 plus square root of 3. Now that we have finished this table, what can you observe? You can see that as x goes from 1, 2, 3, 4, and probably so on, you see that h of x is also increasing in number, in value. 2, 9, 27, 64. So actually, this is the lowest. This is the lowest value that your h of x can take because this is the lowest value that x can take. You can't go at it. You can't evaluate x equals 0 because we are bounded by this. X should be greater than or equal to 1. So this is the lowest x can take. That means this is also the lowest that y can take, or h of x. So our range of h is equal to y, such that y is greater than or equal to 2, greater than or equal to 2, and also where y is equal to h of x. So we're just defining what y looks like, what is the value of y. So it's greater than or equal to 2, and it's just equal to our function. So this one. Your final answers would be this and these for the domain and the range. And with that, we have ended our instructional video for the functions and their graphs on the definition and the evaluation of functions. So